I hope you managed to get PowerView working and managed to look at the results. So now we are going to give you a presentation on the high performance computing capability of Code Saturn. And so basically it's about how to take advantage of high performance computing when using Code Saturn. And he also answers, I hope, some of the questions Jose asks in the chat. So basically, the motivation behind that is that now there's a lot of machines which are petascale machines, and the new exascale machine might come either in June and November this year. So basically, that opens a lot of opportunity for computational fluid dynamics, because we can increase the computational grid size and make the problems much larger to take advantage of these machines. We can also add more physics and more scales in terms of physics to look at much more complicated problems. But there's also the potential for more analysis and more sensitivity analysis based on machine learning, uncertainty quantification, validation and verification, and also artificial intelligence. So there are different techniques to solve the partial differential equations. And for computation fluid dynamics, for instance, you've got mesh-based methods like finite difference, finite volume, finite elements. You might be familiar with some of them. And also meshless methods. One of them, which is very popular in CFD, is smooth particle hydrodynamics. So if you look at all these different techniques, we can split the different stage to solve a problem in about 5 steps. That's the one we haven't identified. So you got either the mesh generation or the initial particle distribution. So what happened when you have, for instance, meshes or particle distribution which are dealing with 7 billion of cells or particles? So that's the question we're going to try to answer. Then, because most of these machines, all these machines are based on distributed memories, you need to distribute the tasks. So, and this is not a straightforward thing to do. Then, of course, you need to solve the PDEs. And at this stage, we have not talked about input output IOs, basically reading from the disk and writing on the disks. So we are going to point out what we think the bottlenecks could be at this stage. And so knowing that MPI IO, which is a flavor of the message passing interface, MPI, has been around for many years and has been tested on a lot of architectures and doing good results, at least for terascale machines. So here's the motivation of the talk, the content of the talk, sorry. So we're discussing a bit about the top 500 machine, the top 500 machine, and some of the machine we've been testing Code Saturn on. Then there's one slide about PRACE, which is a partnership for advanced computing in Europe, which helped us to develop some of the features of the code. We will then give you a short overview of the characteristics of code, which is going to complement what Juan showed you yesterday, then discuss mesh generation, partitioning tools, solving the PDEs, and how to get best of the performance of a machine. and then deal a little bit with I/O management and show, recall the Archer 2 architecture and show how it works. So to test this machine and to assess the performance of this machine, there's a test called Linpack, and then and this gives some basically each machine shows a performance, and they are listed in a top 500 list of machine in the world. And the plot I show you show the list of the evolution of the number one machine from 1994 to 2020, and also the evolution of the last one of this list, the number 500 of this list in blue, which is actually the most important one because it shows that the last one may almost reach the dashed red data, which means that basically the slowest machine of the top 500 is already a petascale machine. So that means that the software need to be adapted to run efficiently on this type of machines. As I said before, the exact flop, which 10 to the power 9 flops, is going to happen this year, probably in June, or probably in June or in November, but definitely this year. And I think for the UK, such a machine is expected for between 2025 and 2026. So here are the top 3 machines in last November. So the fastest one is in Japan. It's called Fugaku, and it's based on ARM chips. And the second and third one are IBM Power 9 machines. The IBM Power 9 now it's a relatively old generation. So the common ground between these 3 machines is that they've got over 1 million cores. And for Fugaku, it doesn't have any accelerator. Basically, the ARM can be seen as an accelerator. But for the 2 machines, the nodes are hybrid with cores and GPUs, and which are accelerators. So the trend for the fastest machine, apart from the ARM features, is to get to get nodes with CPUs and GPUs. So that means that the code have to take advantage of that, and there's a lot of effort at the moment in a scientific community to develop such codes and to optimize them for these new architectures, especially now that the exascale computers will be ready soon. And the last machine here, IBM Mira, is also it was a Blue Gene Q, so this type of machine don't exist anymore. But that's where Code Saturn was tested, not most, but on the largest number of cores. So, as I mentioned before, is that yes, I think William wrote something in the chat about, so Archer 2 is a non-GPU machine and is ranked quite high for CPU-only machines. So in coming back to the presentation, that I shortly mentioned PRACE, which is the Partnership for Advanced Computing in Europe. And PRACE has been running since 2008, and now the last implementation, the sixth one, it's not clear how if there's going to be a seventh one or another type of association such as this one. But through praise, a lot of development has been possible within CodeSatuun, and I'm going to show a couple of them in the next slides. So thinking about the CodeSatuun feature, so is based on a finite volume for arbitrary and structured meshes. It's a mix of C code for maybe for the infrastructure, input-output solvers, and Fortran for some physical models. And Python is used to drive the simulation and for setting up the environment. There's a new discretization which is currently under development, which is a compatible discrete operator, CDO, which aim at improving the robustness of the software and accuracy as well on very distorted grid. So for the physical modeling, I think Juan recalled this. So the code was mainly developed for internal flows with targeting all the flows for nuclear power plants. But since the code has been open source since 2007, many more new physics have been dealt with on it. So the code is very flexible and portable on Unix, Linux, and Macs, and also now on Windows. And one of the important features of the code is that it supports an internal coupling through a library called PLE. And this internal coupling has been used in yesterday's tutorial to couple the fluid and the solid part for and to handle conjugated transfer. So here is a tool chain. So I'm going to try to draw something here on the slide. So yeah, okay. So what I just want to say here is that this bit is all serial in the code. So basically the GUI, the pre-processing stage, is serial. So you could see that one of the log files was called preprocessor.log. So that's where the UNV file yesterday that you had was converted in a format that CodeSatuun could read, and creating the mesh underscore input .csm file. So this was done serial, as well as the XML file reading. Juan said that CodeSatuun doesn't have a mesh generator, so after the input to this bit, so the meshes were pre-processed serially. So I would like to insist on that because because it's serial, it might require a lot of RAM sometimes. But the other part called kernel, this was the original name actually. All this part is actually massively parallel. So that means that mesh modification, mesh and data setup, and mesh partitioning are all parallel, or can be all parallel. And obviously the resolution of the PDEs is also all parallel, as well as output. So now, if you think in terms of mesh generation, and if you enlarge the scope a bit, not only dealing with CodeSatuun finite volume code, for instance, for finite different method, the Cartesian meshes can be generated on the fly. So there's no input there. So everything is in the code and can be massively parallel. However, if you deal with a finite volume, finite element, or meshless method, you might have to input this, you might have to create the mesh first. So CodeSatuun doesn't handle mesh generation, but has got several tools which could help speeding up reading the meshes. So, basically, so an alternative to full mesh generation is can be seen in two ways. So it's instead of having the full mesh, you could generate part of the mesh only independently and glue them into the software. Another way is to generate a coarser mesh and then use a technique called mesh multiplication, so which is basically global mesh refinement to enlarge the size of the meshes. And Juan mentioned earlier that it's now possible in the code to actually run a simulation on a coarse mesh and then multiply the size of the mesh by 8, for instance, in case of hexagonal cells, and interpolate the flow field from the coarse mesh to the big mesh, and restart from that new interpolation. And this saves a lot of compute time. So, but we are going to see first how efficient these mesh tools are. So in terms of mesh joining, the idea is basically, imagine you would be in this situation when you would have a few pipes linked to a vessel, basically. So you could generate independently these two pipes, lateral pipes, and the vessel, and glue them into the code. So the way it works is that at the interface, there's a non-matching, the faces don't match. So new faces are created for the same amount of cells, and this is handled by the code itself. And so, and this is all massively parallel. So it's possible to load independent part of the mesh and or the configuration one by one. And this is due to the fact that most mesh generators are still serial, and so requires a lot of RAM and fat nodes. So the other technique is called mesh multiplication. So the idea is to have several subdivision of each individual elements. So in what's shown here, it works for hexa, tetra, pyramids, and prisms. But another addition has been made to the code for polyhedral cells as well. So, and this, as I said before, allows to magnify the size of the domain. So in terms of tool performance, when you run on distributed memory machine, you've got non-overlapping subdomains, but these non-overlapping subdomains relies on halo or ghost cells to get information from the neighboring subdomains. So computing the halo, so as you can see here, we use massive meshes for 13 billion up to 105 billion. Remember that the simulation you ran yesterday was about 2 million. So this is what 50,000 times larger. But the code is able to handle that. And the way the mesh, the largest mesh was generated was starting from a 26 million cell mesh, and 4 levels of mesh refinement were handled all on the fly. So you only load the 26 million cell mesh, you partition it, and then you refine it 4 times and run the simulation on that. So of course you have to adapt the time steps, but the simulation went fine. So this is not only an exercise just to show what the code is able to do, but the driver behind is that, for instance, EDF would be interested in running a large eddy simulation of a full nuclear reactor. But you would, even for a very, very coarse mesh, and course a large edge simulation, the estimation is probably over several trillion of cells. So this is one of the main drivers to develop this kind of massively parallel codes. And I also wanted to say that the first steps toward mesh multiplication were developed through PRACE by Aleš Ronovský quite some time ago. So now, in terms of timing, basically mesh multiplication is much faster than creating the halo cells, and you see we could run up to 500,000 cores for the 105 billion cell mesh only in 8 seconds, and for the 13 billion cell mesh, even if the mesh multiplication scale, is still much faster than computing the halos. So now that we got the mesh, or got ways to get the mesh, we need to distribute this mesh over the different cores, and because these cores have got a distributed memory. So basically, the principle of partitioning is to try to get the best of the subdivision into subdomains, so have an equal work per subdomain, so which is called load balance. But also you need to have what is called a good edge cut, which means that not all the processors would discuss with each other, but so the processors would actually discuss with neighboring processors as long as non-connective communication is handled. So for this stuff is called having a good edge cut, or basically reducing the interface between for the communication. So when you go toward petascale or exascale, serial partitioning tools only are not enough. So you need to use other tools, and especially, for instance, you could imagine that in some cases, some part of the flow get more costly, and you would need to dynamically repartition. You would not be able to do that for the 105 billion cell case, for instance, if you would use a serial partitioner. So there are two types of partitioning, so graph-based or geometry-based partitioning techniques. So here is an example of a geometry partitioning technique. So imagine this 2D case. So the idea is to go from a 2D or a 3D array to a 1D array. So you're going to go through all the cells and list all the cells in one array, in 1D array. And when you have done that, using the space filling curve Morton Piano or space filling curve Hilbert, so these are different patterns, which are actually be designed to reduce communication between processors, or they are used for that, because the neighbors of each cell is actually very local. So basically, when you've got this 1D array, you can chop it equally in as many number of subdomains as the one you've got for your simulation. So the load balancing in this case is always nearly perfect. I mean, up to 1 or minus 1 cell per subdomain, really. What it might lack is an optimization in terms of interface between processors. So here it looks in real life. So this is these two plots have been colored in function of the MPI task, or MPI rank, as it's called in CodeSation. And this is for the mesh of an extruded square cylinder. So I haven't mentioned much about graph partitioning because the SFC, the space filling curve techniques are embedded into the code, so they come with a release. But the graph-based approaches are third-party libraries that have to be installed separately, and then CodeSaturn has to be installed, accounting for that. So there are two main libraries: Scotch, PT-Scotch, which is one, and Metis Parametis, which is the second one, and they are based on graph partitioning. So if you see, so the plots here show the colors of the per MPI rank, and you can see that PT-Scotch and space filling curve Hilbert are quite regular. However, if the initial numbering is really poor, and you don't take any action, you get this mix of color on the bottom slides. And this means that all the processors are going to talk to each other. In the case of the, I mean, I'm talking about sample send and receive simulation communication, so not the collective ones. However, for PT-Scotch and Hilbert, you can see that the colors are very well distributed, and they're going to limit communication. So you expect that the two first one are going to be much faster than I mean, that CodeSaturn is going to be much faster when you use the two top partitioner rather than the bottom one. So now solving the PDEs is that there are basically two types of PDEs. There are time explicit and time implicit. So we're not going to look at time explicit here because CodeSaturn is a time implicit code mainly. Time implicit means that matrices have to be solved, and time explicit means that actually the matching in time is such that the discretization is very local. So we focus here on incompressible CFD, so that's why we use time implicit, and we use matrix based resolution. So if not handled properly, computing the pressure itself can take up to 60% of the full time step. And because the code has been optimized a lot, now it's reduced to probably 20–30%. So, and that's to answer Jose's question earlier. So the code has been tested for large domains and meshes. So, and Duquin used to be a blue gene queue as well, same as Mira. And the code showed nearly perfect scalability up to the full size of the machine, which was more than 1.8 million threads, I think, and was and could join a club which was called the IQ Club for very, very fast and scalable machines. And if you look at the results on the right-hand side now for Mira, for the 105 billion cells, basically the speed up here is defined as that if when you double the number of cores, an ideal speed up would mean that you would double. No, you would halve the time to solution, and this is what happened when you go from 500,000 to about 1 million threads, and going from 500,000 threads to 3 million threads. The code is about 3 times faster. So that's what is highlighted in red. Now, the previous results are shown here again at the bottom, and just to show the efficiency, but similar efficiency is observed on a machine called Hawk, which is very similar to Archer 2 and has been tested up to 500,000 MPI tasks and with an efficiency of 92%. So basically that means the code is scales very, very well and this is achieved because to solve the pressure a multigrid is used as a preconditioner and a conjugate gradient is used as a solver, the conjugate gradient being well known to scale very well. So, but there's always a push in Code Saturn to get very good scalability, because if you remember well, I mean, the aim would be to be able to run on, meshes over a trillion of cells, and these cells having any shape, if possible. So this was scalability presentation and efficiency of the performance, but something shouldn't be discarded is the accuracy of the code. So a test case which is used for that is a Taylor Green Vortex test case, and the code has been tested from 64 cube to 2048 cube, which represents a 7 or 8 billion mesh. So this was run for production, while the other tests were run just for a few time steps. So you can see that for the 2048 cube, Code Saturn matches the spectral reference, which is the best reference you could actually, the best data you could actually get. And this data are shown as dots on the pictures. So basically, this test case is about an initial solution, and because of periodic boundary condition, during the course of the simulation, basically the flow, the flow and the vortices vanish. And this test case is used to assess the accuracy of numerical schemes. I forgot to say that the code is that finite value code is second order in space and time in this case. So now, I said before that the trend for the new machine are nodes which are made of CPUs and accelerators GPUs. So there are many more cores than there used to be, 128 for Archer 2 and also some Power 9 machines, and sometimes 4 or 6 GPUs. And most of the performance is achieved from or will be achieved from the GPU nowadays. For communicating between CPUs and GPUs is actually an issue, because it can take much more time than running on the GPU itself. So for Code Saturn, there have been several attempts to develop GPUs, but none of them have made the official release yet. Fortunately, version 7.2 or 7.3, so which are going to be released in June or December, will support multi-GPUs. So that was an attempt carried out by Samuel Ontao from IBM Research, and it was for a very simple case, and it was run in Oak Ridge on Summit, basically the second machine in the world, up to 512 nodes of the machine, and each of the nodes have got 6 GPUs. And they got each of the nodes got 42 cores. So it was observed that about a speed up between 2 to 3 was observed compared to CPU only, which is in the range of what similar software use. I mean, shows, sorry. So now, thinking about the IOs is that if you generate, you remember that Juan showed you the post-processing file. Actually, for the 2 million cases, the post-processing folder is already 250 megabyte big. So if you imagine that you have to dump that on the disk about 10,000 times to generate a mesh, I mean, you end up with several terabytes of data just for this simple case, which is only 2 million large. So this is not a manageable solution for going for a billion of cells. So a way to manage this data is actually either to generate frames or on a much coarser grid and dump that on the disk, or use a visualization library and coprocessing. So we're going to show a bit the principle, how it works during the last tutorial. So if we want to generate films, there's a solution. For the monitoring points and probes as well, they are just a small ASCII files, so that's very easy to do. The thing which is actually the main bottleneck is the checkpointing and restarting, and this is not only for code Saturn, it's for any code. So because you've got a queuing system with, for instance, if you get a 36-hour simulation and you've got queuing system which forces you to use only 12 hours. At the end of the 12 hours, you need to dump data on the disk and then read them again for the next 12 hours. And this has to be done in an efficient way. And there are, I mean, that we know there are not many ways around. So the parallel I/O has been tested. So by writing on the disk 20 terabyte mesh. That was for the 105 billion cell mesh. If you remember what you had in your folder, in a simulation folder, you had a mesh input file and you had a mesh output file. So this is a mesh output file which has been dumped on the disk. So and dumping this on the disk first was doable. So it takes a little bit of time, but at this scale, it's normal because it takes about 40 minutes, but you do it only once. However, the checkpointing bits, which was done at that time, was done in 10 to 15 minutes, knowing that the time step was about 20 to 30 seconds. So that doesn't correspond to time step. So this is also manageable. So now, a summary. So the step to run a simulation that we identified actually well dealt by Code Saturn, and if not now, this is in progress. For instance, like the GPU implementation. And the main drawback, which is the same for all the software, is going to be the checkpointing and restarting procedure. So that's why I/O is really something to look at in the future, even if MPI/I/O is doing a great job. And finally, I just recall how Archer 2 works, and this big machine usually works. So you got logging nodes where you got access to the home and the work directory. And from the work directory, you can go to compute nodes and submit a job there and recover the results on the work directory and copy them back locally to interpret them. So I think that's it for me. So have you got any questions? If there are no questions, maybe we can move to the next tutorial then, which is about performance assessment. Okay, so you can find this file If you just give me a second.
It's on the one drive shared folder with all the other files.
Okay. Okay, fine. Okay, thanks, Juan. So assuming assuming you got the file, so basically this tutorial is a little bit different because we are going to use user subroutine to use different partitioner and to run very small simulation, short simulation of the case you were running yesterday, and for just 100 time step to see if there's any influence on the time to solution depending on the partitioner you're using. So that's the first part of the tutorial. The second part of the tutorial is to use MPI for the distributed memory part of the code and OpenMP for the shared memory part of the code. So this tutorial, I mean, because we are not, let's say, in a critical situation, it's going to be difficult to draw some conclusion depending on the from the results you are going to get. But this is to show that this is doable in code saturation. So first of all, and it is very, very important, don't use code_saturation to create your case, but use code_saturation with libs. This is it. So the reason for that is because that version with libs has got the partitioners installed in it, and the other one doesn't. So if you use code saturation only, you cannot run the first part of the tutorial. So I will let you go through the tutorial. So on page 2, you can see that you create you create the, how's it called, the case from the previous case with minus copy minus from, yeah. And so because you're going to use the same settings apart from some user subroutines. So yes, I think you could have a go at it, and please let us know how it goes. At the end of each section, you've got some timings which are just there to give you a flavor of what you could get. You will never be able to get exactly the same timings, but it should be the same order of magnitude for sure. So if you got any issue, just use the chat, please.